This week, satellites orbiting 400 kilometers above the Pacific Ocean detected something that is keeping every seismologist on the planet awake at night. Instruments built to measure the movement of stars were suddenly redirected toward a single strip of seafloor off the coast of Japan. Because this week, the ocean floor cracked open along the most dangerous fault line on Earth. And right now, no one, not a single scientist, not a single government agency, not a single orbital sensor system humanity has ever built, can answer the one question that matters. Was that earthquake the disaster, or was it just the warning? 15 years ago, this exact fault system gave the world a warning. Nobody recognized it as a warning. 51 hours later, nearly 20,000 people were dead. 3 nuclear reactors were melting into the ground, and a wall of water tall enough to swallow an 8-story building was erasing entire cities from the map of Japan. The warning had come first. The catastrophe had come second. And the terrifying truth that every seismologist is sitting with right now, tonight, as the aftershocks continue rolling through the crust beneath the Pacific, is this. We are back inside that window. The same fault, the same mechanism, the same magnitude, the same geography, and the same unbearable uncertainty about whether what just happened was the main event or the opening act of something far, far worse. This is not a story about an earthquake that happened. This is a story about an earthquake that may not be finished happening. Let that sit with you for a moment, because understanding why that statement is scientifically defensible and not just sensationalism requires understanding something about how fault systems work, how the Earth stores energy, and how the most sophisticated monitoring network in human history, a network that includes dozens of satellites, hundreds of seafloor sensors, and GPS stations precise enough to detect the ground moving by the width of a human hair, is right now staring at data that it cannot yet fully interpret. The answer to the most important question in seismology tonight is already encoded in the rocks beneath the Pacific. The decision has already been made by the fault. We just cannot read it yet. And when we finally can, it will either be because enough time has passed that we exhale and call it over, or because the ground beneath northeastern Japan has moved again, and this time moved in a way that makes what happened this week look like a tremor. To understand what is at stake, you need to understand the machine that is running beneath the floor of the Pacific Ocean. The Japan Trench is not simply a crack in the seafloor. It is the surface expression of one of the most violent geological processes on this planet. 2 tectonic plates are meeting here. The Pacific Plate, an ancient slab of oceanic crust covering an area larger than all of the continents combined, is diving beneath the North American plate at a rate of about 8 to 9 centimeters per year. That sounds slow. In human terms, it is slow, but tectonic time is not human time. Over decades, 8 centimeters per year becomes meters. Over centuries, it becomes tens of meters. And every single millimeter of that motion is storing energy inside the rocks at the boundary between the 2 plates, energy that cannot be released gradually, energy that must eventually be released all at once, in a single catastrophic rupture, in an earthquake. The plate is always pushing, the fault is always resisting. The rocks at the interface are locked together by friction, holding, until one day they cannot hold anymore, and when they let go, they do not let go gently. This week, a section of that interface let go. The ground 100 kilometers east of the coast of Honshu slipped. The rupture occurred at a depth of approximately 11 kilometers below the seafloor. That number matters enormously, because at 11 kilometers of depth, there is almost no rock between the rupture and the ocean above it. The energy from the slip reached the water column almost instantaneously. The seafloor moved upward. The ocean above it moved upward with it. And the pressure wave that created began traveling outward in every direction at the speed of sound through seawater. Within minutes, the Japan Meteorological Agency's automated tsunami prediction systems had classified the event as tsunami generating and issued warnings across 3 prefectures: Iwate, Miyagi, and Aomori. Evacuation orders went out, not suggestions, orders. Because in Japan, 15 years after the worst tsunami disaster in modern history, nobody waits to see how big the wave is before they tell people to run. The first waves that arrived measured about 40 centimeters, a little over a foot of water rising against the harbor walls. If you were watching the camera feeds from the coast, you might have felt a moment of relief. That does not look so bad. That is almost nothing. Why are they still evacuating? And this is exactly the thought that has killed people on this coastline before. Because tsunamis do not arrive as a single wave. They arrive as a train of waves. The first wave is almost never the largest. The second or third or fourth wave can be double, triple, quadruple the height of the first. The ocean is not finished with you just because the first surge was small. The energy is still propagating. The waves are still building. And in the narrow bays and funnel-shaped inlets of the Sanriku coast, a wave that measured 40 centimeters offshore can arrive at the head of the bay as something 5 or 10 times that height. Japan knows this. Japan learned it in the worst possible way. And so nobody on that coast made the mistake of assuming the danger had passed because the first measurement was modest. Simultaneously, an entirely separate protocol activated without anyone needing to call for it. Nuclear facility inspections. 5 plants were assessed immediately, including the facility whose name still carries a weight that no amount of time has fully diminished. Fukushima Daiichi. Inspectors moved through each site checking cooling systems, containment structures, spent fuel pool levels, emergency generators, and the status of ongoing decommissioning work. No abnormalities were detected. The systems held, but the very fact that this happens automatically, that there is no phone call that needs to be made, no decision that needs to be taken, that the protocol simply executes the moment a major earthquake strikes this fault system, tells you everything about the shadow that 2011 still casts over every decision made in northeastern Japan. This is not a country that gambles on nuclear safety anymore, not after what it lost. Train lines stopped, the Tōhoku Shinkansen halted, power outages moved through coastal communities, roads cracked, landslides came down from rain-softened hillsides. The immediate damage was real, but it was manageable. This was not the kind of event that breaks a civilization. And yet the scientists were not relieved. They were not saying the worst was over. They were saying, in the careful and measured language that scientists use when they are genuinely frightened, that the public should remain on high alert for the next 7 days, that aftershocks of similar magnitude were possible, that no one should return to low-lying coastal areas until further notice. 7 days, not hours, days. Because this earthquake did not happen somewhere random. It happened on the Japan Trench, the same subduction interface that 15 years ago produced a magnitude 9.1 rupture that remains among the most powerful earthquakes ever recorded on the surface of this planet. And the specific location of this week's earthquake is not just on the same fault system in a general sense. It sits in a region that hazard models have been flagging for years as a zone of particular concern. A zone where strain has been accumulating, where the slip deficit, the gap between how much the plates have moved and how much of that movement has been released as earthquakes, has been growing year after year since 2011. And that brings us to the question that nobody wants to say out loud. 15 years ago, 2 days before the magnitude 9.1 destroyed northeastern Japan, there was a magnitude 7.3 earthquake on this same fault system. The seismologists logged it, they analyzed it, they issued standard advisories, and then the news cycle moved on. 51 hours later, the main shock arrived. In hindsight, the 7.3 was a foreshock. In real time, nobody called it, because in real time, you cannot call it. The science of distinguishing a foreshock from a standalone earthquake, while it is happening, does not yet exist. The only way to know a foreshock was a foreshock is to wait for the larger earthquake to follow it. This week's earthquake came in at a magnitude between 7.4 and 7.5. That is remarkably close to the magnitude of the 2011 foreshock. The depth profile is similar, the fault system is the same, the mechanism is similar, and the region where it struck has been identified by multiple independent research groups as being under significant accumulated strain. The earthquake happened, the question is whether the earthquake is finished. Now, to be precise in a way that matters, this week's earthquake did not occur at the exact same location as the 2011 foreshock. The epicenter is offset to the north, a different segment of the fault, a different patch of the interface, so this is not a carbon copy of what happened 15 years ago. The 2011 rupture was a massive elongated patch, roughly 500 kilometers long, running down the subduction interface offshore of Miyagi and Fukushima prefectures. The seafloor in some places slipped by as much as 50 meters. That is the height of a 16-story building of sudden displacement along a single fault surface. This week's event is not that, not yet, but it is the same fault family, the same tectonic architecture, and that matters in a very specific way. When the 2011 rupture occurred, it released an enormous amount of accumulated strain, but only along its specific patch. The segments immediately to the north and south of that patch did not slip. They remained locked. They continued accumulating strain as the Pacific plate kept pushing. And in the 15 years since, those locked segments have been identified in study after study as regions of elevated hazard, regions where the debt of accumulated motion has not yet been paid, where the tectonic energy is still stored, still waiting. This week's earthquake occurred in one of those regions. The question scientists are now racing to answer is whether this event released a significant portion of that accumulated strain, or whether it released only a small portion and in the process transferred stress to adjacent locked segments, pushing them closer to their own failure point, because those are two completely different outcomes. In the first scenario, the fault system is in a safer state tonight than it was last week. The debt has been partially paid. the spring has partially unwound. In the second scenario, the fault system is in a more dangerous state tonight than it was last week. The stress has moved, but it has not been eliminated. It has relocated to a section of the fault that had not yet broken. We do not know which scenario we are in. The modeling takes time. The GPS analysis takes time. And in the meantime, every instrument humanity has deployed to watch this fault system is running at full capacity, feeding data into institutions that are trying with everything they have to read the answer before it declares itself. Let me tell you about one of those instruments, because it represents something that did not exist when the 2011 disaster happened, and whose presence changes everything about how we are watching this week's event. Orbiting the Earth right now is a constellation of synthetic aperture radar satellites. These are spacecraft that emit microwave pulses toward the Earth's surface and measure the reflected signal with extraordinary precision. By comparing radar images taken before an earthquake with images taken after, scientists can map exactly how the ground moved during the rupture, not just approximately, not just in the general direction of motion, but down to centimeters across entire regions from space. The European Space Agency's Sentinel satellites are contributing data to this analysis. Japan's own ALOS-2 radar satellite is contributing data. Commercial Earth observation platforms are contributing data. Together, they are constructing a three-dimensional picture of the crustal deformation caused by this week's rupture. That picture will take a few days to fully assemble, but when it does, it will tell scientists not just how much the ground moved, but which parts of the fault interface slipped, in which direction, by how much, and where the stress was transferred. This is the kind of analysis that in 2011 took months. It is now being done in days, and the results will feed directly into the critical calculation that determines whether adjacent fault segments are now closer to failure than they were before this week's earthquake. From space, the Earth's surface is an open book. The problem is that the most important information is written not on the surface but in the rocks below it, and those rocks are telling a story that even our most advanced orbital sensors cannot fully read. GPS satellites are part of this picture too. Japan operates one of the densest GPS monitoring networks in the world, called JANET, and every station in that network is streaming position data continuously, updated several times per second, accurate to millimeters. In the days before the 2011 earthquake, those GPS stations recorded something that was only recognized in hindsight, a slow slip event. The fault was moving silently, releasing strain in a way that produced no felt shaking, no seismic waves that standard instruments could easily detect, but measurable ground deformation. The fault was creeping, and that creeping was a precursor to the catastrophic rupture that followed. Right now, scientists are looking at the GPS data from the stations surrounding this week's rupture zone and asking the same question. Is there any anomalous motion, any silent slip, any gradual drift that falls outside the expected pattern of post-earthquake relaxation? Because if the answer is yes, if the fault is moving silently right now in addition to the shaking that has already been felt, that changes the risk assessment significantly. The GPS data is being analyzed in real time, and the answer to that question, if it is clear enough to answer, will be one of the most consequential pieces of scientific information produced this week. Now let me tell you about something called the aftershock sequence, because the behavior of aftershocks since this week's main event is one of the things that is most concerning the scientific community right now. When a large earthquake occurs, it is followed by a series of smaller earthquakes as the rocks around the rupture adjust to their new positions. These aftershocks follow a predictable pattern. There is a burst of activity immediately after the main event, and then the rate of aftershocks decays over time. The curve drops off. The system settles. Japanese seismologist Fukushima Daiichi documented this decay pattern in the 1890s, and it has since been observed in earthquake sequences all over the world with remarkable consistency. You get the main shock, you get the spike of aftershocks, and then the rate of activity decreases according to a predictable mathematical relationship. What is happening along the Japan Trench this week is not that. Within 7 hours of the main shock, the region recorded more than 14 earthquakes of magnitude 4.5 or greater. That is significantly more than you would expect in the first 7 hours of a typical magnitude 7.5 aftershock sequence, based on historical averages from similar subduction zone events. The distribution of aftershocks that would normally be spread across 24 to 48 hours was instead compressed into a single 7-hour window. That is what scientists mean when they say the aftershock sequence is accelerated, and it is not just the number of events, it is the energy. Multiple aftershocks came in at magnitude 5 or greater within hours of the main event. Aftershock magnitudes are generally supposed to be smaller than the main shock by a predictable margin. Getting one large aftershock is normal. Getting multiple magnitude 5 plus events in rapid succession is a signal that the system is still releasing significant energy rather than gently decaying. But there is one specific aftershock that has the scientific community paying particular attention. A magnitude 5.6 event that occurred at a depth of only about 2.2 kilometers below the seafloor. That is extraordinarily shallow. For reference, most aftershocks along a subduction interface occur at depths of 30 to 60 kilometers because that is where the main interface itself sits. An aftershock at 2.2 kilometers depth is not occurring on the main interface. It is occurring in the overlying plate, extremely close to the seafloor. And here is why that matters in a way that goes beyond simple statistics. Shallow aftershocks, especially shallow offshore aftershocks, have the capacity to generate their own tsunamis independent of the main event. The shallower the slip, the more directly it displaces the water column above it. When you are already in a situation where coastal communities are sheltering in evacuation areas and tsunami warnings have not yet been fully lifted, a shallow near-seafloor aftershock is not a statistical curiosity. It is a second independent threat. It also raises a deeper question about the mechanism, because at 2.2 kilometers below the seafloor, you are in the domain of what geologists call splay faults. These are secondary faults that branch off the main subduction interface and rise upward toward the seafloor at a steeper angle. They are particularly dangerous because they are among the most efficient generators of large tsunami waves. When a splay fault slips, it displaces the seafloor so directly and so efficiently that it can produce a tsunami disproportionately large relative to the magnitude of the earthquake that caused it. Research into historical megatsunami events has suggested that some of the most catastrophic waves ever recorded were amplified not by the main rupture alone, but by simultaneous activation of splay faults branching off the main interface. If the aftershock sequence this week is activating splay faults, that is not a sign of a system winding down. That is a sign of a system that is still redistributing stress, still negotiating the consequences of the main rupture, still in motion. Some scientists will rightly point out that aftershock sequences sometimes just behave unusually. Natural systems have variance. Not every decay curve follows the textbook average. Sometimes a sequence is front-loaded without that meaning anything ominous. The fact that the aftershock activity is elevated does not automatically mean a larger event is coming. It might be statistical noise within a sequence that ultimately winds down normally. But here is what makes it impossible to simply dismiss. In the 2011 sequence, when researchers went back and analyzed the foreshock data in detail after the disaster, they found something striking. The foreshock sequence had shown unusual clustering. The rate of small earthquakes had been higher than expected in the hours and days before the magnitude 9.1. The epicenters of successive earthquakes had been migrating, slowly drifting in a specific direction toward the area where the main rupture would eventually initiate. Those signals were there, they were in the data. In real time, they were not recognized. In hindsight, they were unmistakable. Scientists right now are looking at this week's aftershock sequence and asking whether it shows similar migration, whether the epicenters of successive aftershocks are drifting in any particular direction, whether they are clustering at a boundary between a ruptured segment and a still locked segment, as if energy is piling up against a barrier that has not yet given way. It is too early to say definitively. The sequence needs more hours, probably more days, before a clear migration pattern becomes visible if one exists. But the question is being asked with the urgency that comes from knowing what was missed 15 years ago. Every hour that passes adds more data. Every aftershock that is recorded contributes to a picture that is slowly, agonizingly slowly, coming into focus. Now let me take you even further out from the immediate scene of this week's earthquake, because there is a broader context that makes this week's event even more difficult to interpret. This is not the first major earthquake to strike the Japan Trench in recent months. A few months ago, a magnitude 7.6 earthquake struck near Aomori in northern Honshu. It was offshore. It was within the Japan Trench system. It produced a tsunami warning that was eventually lifted. Damage was limited, and after the usual period of news coverage, it was logged and largely forgotten by the public. The long-term average interval between magnitude 7+ earthquakes in the Japan Trench region, based on decades of historical data, is approximately 16 months. Two major events within just a few months is on the shorter end of what has historically been observed. It is not unprecedented, but it represents a tighter clustering than the average would predict. When earthquake sequences cluster in time like this, scientists ask a specific question. Is the clustering random or is it meaningful? Random clustering is a real phenomenon. If you flip a coin 100 times, you will get runs of heads and tails that look like patterns but are just statistical variation. Earthquake sequences can do the same thing. Two major events close together in time does not automatically mean they are connected. But sometimes the clustering is not random. Sometimes one earthquake influences the stress state of the surrounding region in ways that elevate the probability of subsequent events. This is well documented. Large earthquakes are followed by elevated rates of seismic activity, not just in their immediate aftershock zones, but on connected fault segments throughout the broader region. The system enters an active phase, and that active phase can persist for months or years. The Japan Trench has been in a period of adjustment since 2011. The magnitude 9.1 rupture released an enormous amount of stress, but also rearranged the stress field across the entire northern Japan subduction zone. In the 15 years since, the system has been slowly renegotiating that arrangement. Smaller earthquakes, slow slip events, gradual deformation. The machinery has never fully stopped moving. And when scientists look at the recent clustering of major events, they are asking whether the system is entering a more active phase of that adjustment, a phase in which the probability of another major event in the coming months is elevated compared to the long-term baseline. This would not necessarily mean a magnitude 9 is imminent. It would not mean catastrophe is inevitable, but it would mean that the quiet period that followed 2011 may be giving way to something more active, and that the odds of another significant earthquake in this system are higher today than they were 2 years ago. There is another layer to this story that sits above the surface of the Earth rather than below it, and while it is more speculative, it is part of the scientific conversation happening this week. Approximately 23 hours before this week's earthquake, a G2 geomagnetic storm struck the Earth. G2 is a moderate storm on the 5-point scale used by space weather agencies. It was associated with elevated solar wind activity, increased electron flux in the magnetosphere, and aurora displays visible at lower latitudes than usual. Satellite operators made routine adjustments. The storm was notable but not exceptional. The question of whether space weather events can influence earthquake timing is one of the most contested topics at the intersection of geophysics and space science. The mainstream position among seismologists is that no established physical mechanism connects geomagnetic storms to earthquake occurrence. Earthquakes result from stress accumulated over decades in the Earth's crust, driven by tectonic forces orders of magnitude more powerful than any electromagnetic influence from the sun. The energy mismatch between a geomagnetic storm and a subduction zone fault is staggering. The storm is whisper, the fault is thunder. But a minority of researchers has been publishing statistical analyses suggesting that earthquake occurrence rates show subtle correlations with space weather events. Not that storms cause earthquakes, but that they might act as triggers for faults that are already on the verge of failure. The distinction matters. A trigger does not create the energy. The energy was already there, stored in the rocks over decades. A trigger merely provides the small perturbation that pushes a system, already near its failure threshold, over the edge. The fault was going to rupture eventually. The question is whether external electromagnetic influences can determine precisely when eventually becomes now. These studies are contested. Some find suggestive correlations, others find none. The proposed mechanism of capacitive coupling, where geomagnetically induced electric currents in the Earth's crust alter stress or fluid pressure on faults near failure, is physically plausible but has not been rigorously demonstrated. The scientific community is genuinely undecided. Tonight, a G2 storm preceded a major earthquake on a highly stressed fault system by 23 hours. One data point is not a pattern. A correlation between two events does not establish causation. And there are hundreds of earthquakes happening globally every day, so finding any earthquake that followed any space weather event is trivially easy. But we are sitting this week inside a situation where the fault was already stressed, where the slip deficit had been accumulating for years, where hazard models had flagged this region as elevated risk. If external triggers have any role at all in fault rupture timing, this was a system that did not need much of a push. And whatever happened above the Earth this week happened very close in time to what happened below it. The connection may be nothing, it probably is nothing. But the uncertainty around it is real, and the uncertainty is part of the story. What is definitely not nothing is the physical geography of the coastline that sits above this fault system. The Sanriku Coast, the stretch of northeastern Japan that runs along the Pacific side of Iwate, Miyagi, and Aomori prefectures, is one of the most naturally dangerous coastlines for tsunamis anywhere on Earth, and understanding why requires understanding something about the shape of the land itself. The Sanriku Coast is a ria coast. Its bays are drowned river valleys. The inlets are narrow and funnel-shaped. When a tsunami wave enters one of these bays, the water has nowhere to go but up. The wave height increases dramatically as the bay narrows toward its head. A wave that measured 1 meter in open water can arrive at a coastal village as a 10-meter wall of moving ocean. The coastline is not just a target, it is a wave amplifier. This is not new information. This coastline has been producing catastrophic tsunamis throughout recorded history. In 1896, an earthquake offshore generated a tsunami that was felt as only mild shaking along the coast. Fishermen continued working. Families sat down to dinner. And then the ocean withdrew, and 20 to 40 minutes after the shaking, a wave the height of a 12-story building erased villages and killed approximately 22,000 people. In 1933, another earthquake, different mechanism, similar result. Thousands dead, thousands of homes destroyed, the same coastline, the same amplifying geometry. When Japanese authorities reacted to this week's earthquake with the speed and intensity that they did, they were not overreacting. They were reacting to a coastline that has repeatedly proven it can take a modest offshore event and turn it into something incomprehensible by the time the water reaches the shore. The 40-centimeter first wave that arrived at the harbor walls this week was not reassuring to anyone who understood this history. It was a reminder that the ocean was not finished measuring itself. Now let me be honest with you about something that the official communications around this week's earthquake cannot fully convey. There is a gap between the language that government agencies use when issuing public advisories and the conversation that is happening right now among the scientists who study this fault system. Official advisories are calibrated for public communication. They are designed to promote preparedness without causing panic. They use standard language. They reference 7-day alert periods. They remind people to stay away from coastal areas. They do not use the word foreshock. They do not acknowledge directly that this week's event might be the opening act of something much larger. Because using that language publicly, without certainty, risks creating panic for an event that statistically is most likely a standalone earthquake. The scientists are having a different conversation. The researchers who have spent their careers modeling the Japan Trench, who have analyzed the 2011 sequence in microscopic detail, who understand the slip deficit data and the stress transfer calculations, who have access to the real-time GPS and seismic feeds, those scientists are not sleeping easily this week. They are watching data feeds at hours when they should be in bed. They are calling colleagues in different time zones. They are cross-checking what they are seeing against historical analogues. They are asking each other in measured, careful tones whether the signals they are observing match anything they have seen before. This is what information asymmetry looks like in real time. The data is largely public. The seismic network feeds are accessible to anyone with the right software. But the ability to interpret that data, to recognize what is signal and what is noise, to know what a particular aftershock depth distribution means, or what an unusual rate of moment release implies, that requires years of specialized training and pattern recognition that cannot be quickly summarized in a press release. So let me try to bridge that gap. Let me tell you what the scientists are actually watching in plain language so that you can look at the same signals they are. The first thing they are monitoring is something called hypocenter migration. Every aftershock has a specific location in three-dimensional space: latitude, longitude, and depth. If you plot those locations over time, you can see whether the earthquakes are clustering in one area or drifting somewhere. If they are drifting, the direction of the drift is critical. Are the epicenters moving toward shallower parts of the fault? Are they marching along the fault toward one end of the rupture zone? Are they clustering against a specific boundary, as if energy is piling up against a section of fault that has not yet released? In 2011, retrospective analysis of the foreshock sequence revealed clear migration of epicenters in the days before the magnitude 9.1. The small earthquakes were moving, tracking in a direction that in hindsight pointed directly toward where the main rupture would begin. That pattern was in the data. Nobody saw it in time to act on it. Scientists are watching this week's aftershock sequence, specifically for any sign of similar migration. The second thing they are monitoring is total moment release. Seismic moment is a measure of the total energy released by an earthquake. When you add up the moment from the main shock and all of its aftershocks, you can compare the total to what you would expect from an event of this magnitude. If the total energy being released is significantly larger than the expected amount, that is a sign that the system is not simply settling after a single rupture. It is a sign that there may be more strain being released than the single event should account for, which could mean that the rupture was not fully completed, that there is elastic strain in the surrounding rocks still seeking release. The third and perhaps most important signal is the GPS deformation data. Scientists are looking at every station in the Jeanette network for anomalous motion. Any sudden jump that would indicate fault slip. Any slow gradual drift that would indicate a slow slip event is occurring. Any pattern of motion across multiple stations that would suggest the crust is deforming in ways inconsistent with normal post-earthquake relaxation. If the GPS data shows anomalous deformation, that changes the picture dramatically. And the fourth signal is the moment tensor analysis of each significant aftershock. The moment tensor is a mathematical description of the mechanism of a rupture. It tells you the orientation of the fault, the direction of slip, the style of faulting. By analyzing the moment tensors of the larger aftershocks, scientists can determine whether the stress is being released on the main subduction interface, on splay faults, on secondary structures, or on entirely separate fault systems. Each answer has different implications for the ongoing hazard assessment. All four of these analyses are happening simultaneously right now, in real time, being fed by data streaming in from hundreds of sensors on the ground, on the seafloor, and in orbit. And here is what makes this moment so historically unusual. In 2011, most of these analytical tools existed in theoretical form. The GPS network existed, the seismic network existed, the satellite technology existed in early form, but the pipelines for integrating all of this data in real time and producing meaningful interpretations quickly enough to influence decisions, those pipelines were not yet built. They are built now. The scientific infrastructure watching this week's event is qualitatively different from anything that existed 15 years ago. Data that used to take months to analyze is being processed in hours. Satellite images that used to require weeks of manual processing are being generated semi-automatically. Stress transfer models that used to require dedicated supercomputer runs are now executing on workstations in university offices overnight. We are more capable of watching this fault system than we have ever been. The monitoring network is denser. The instruments are more precise. The analysis pipelines are faster. The communication between institutions is better. If this week's earthquake is a foreshock, we have a greater chance of recognizing the precursor signals before the main event than humanity has ever had in any previous similar situation. And that is both extraordinarily encouraging and deeply sobering, because if all of this technology, all of this capability, all of this monitoring is still not enough to give us certainty about whether we are watching a foreshock sequence or a standalone event, that tells you something profound about the limits of what we actually know. The rocks beneath the Pacific do not care about our monitoring networks. The fault does not consult our hazard models. The tectonic machinery that is running right now beneath the floor of the ocean has been running for hundreds of millions of years. It was running before the first human ever looked at a hillside and wondered why the stone layers were tilted. It will be running long after every instrument we have ever built has gone silent. Our ability to watch it has improved immensely. Our ability to predict what it will do next has improved marginally. We can see what is happening. We often cannot tell what it means. The gap between observation and understanding is the gap we are living inside right now, and it may be the most important gap in all of science. Let me now be explicit about the range of possible futures that we are looking at, because being clear about this is more useful than being either falsely reassuring or falsely alarming. The most likely outcome by base rate probability is that this week's earthquake was the main event. Most magnitude 7+ earthquakes in any subduction zone are not foreshocks. They are the primary rupture, followed by a declining sequence of aftershocks that gradually fade over weeks and months. Statistically, this is what happens the overwhelming majority of the time. The early aftershock activity settles into a normal decay pattern. The GPS stations show routine post-earthquake relaxation. The fault system quiets. The Sanraku coast returns to its rhythms. The probability of this scenario is probably somewhere between 70 and 85%, depending on how much weight you give to the unusual features of the aftershock sequence and the geological context. That is the most likely future. Hold on to that number. The second possible future is that this week's earthquake was a foreshock, that within hours or days or weeks, the Japan Trench produces a second, larger earthquake, magnitude 8 or greater, possibly approaching magnitude 9. In this scenario, everything that has happened this week will be retrospectively understood as the precursor sequence. The unusual aftershock activity, the shallow splay fault event, the migration of epicenters, these will be understood in hindsight as the fingerprints of a system that was winding up rather than winding down. The probability of this scenario is low in absolute terms. Estimates would vary between 2 and 10% depending on the specific assumptions used. That is not a high probability in everyday terms. But it is high enough to justify every precautionary measure that Japan has taken this week and is continuing to take. A 5% chance of a magnitude 9 earthquake is not something you ignore. It is something you prepare for with everything you have. The third possible future is what might be called the multi-event stress cycle. In this scenario, neither of the above happens in the near term. Instead, this week's earthquake is one event in a sequence of major earthquakes that will play out over months or years as the Japan Trench continues redistributing the stress that has been building since 2011. No single catastrophic event. but a prolonged period of elevated activity, with multiple major earthquakes striking different segments of the fault system at irregular intervals, each one releasing some of the accumulated strain and transferring some to neighboring locked segments, slowly working through the tectonic debt that 15 years of continued plate motion has accumulated since the last mega-rupture. This scenario is harder to evaluate probabilistically because it unfolds over such a long time scale, but it is arguably the most scientifically grounded of the three because it is consistent with what we know about how fault systems behave in the decades following a magnitude 9 rupture. They do not simply go quiet, they renegotiate, and that renegotiation can produce elevated seismic activity for years. All three scenarios are consistent with the data currently available. None of them can be ruled out. The answer is not in the numbers. The answer is not in the press releases. The answer is in the rocks, already decided, already encoded in the current stress state of the subduction interface, waiting to be read. And we cannot read it yet. What we can do is watch. What we can do is maintain the preparedness that Japan has so clearly and painfully earned. What we can do is respect the history of this coastline, a history that has repeatedly demonstrated that the first signal is not always the full story, that the modest initial wave is not necessarily the largest wave, that the manageable early damage does not necessarily represent the final toll. The Sanraku coast has been teaching this lesson for over 100 years. In 1896 it taught it. In 1933 it taught it again. In 2011 it taught it in the most devastating way imaginable. The lesson is written into the geography, into the shape of the bays, into the height markings on the concrete walls that now line the coast, into the stone monuments placed by survivors of past tsunamis on hillsides above the water line, with inscriptions that say do not build your homes below this point. This week, Japan is reading those monuments with the attention they deserve. There is something profound about watching a society respond to this kind of uncertainty. The aggressive warnings issued within minutes and sustained for hours after the first small waves arrived, the automatic nuclear inspections, the 7-day elevated advisory, the continuous monitoring, the refusal to say everything is fine just because the visible damage is limited. All of it is the institutionalized memory of what was lost last time. All of it is a collective refusal to be surprised again. But even with all of that preparedness, even with all of that institutional wisdom, even with satellites overhead and seafloor sensors below, and GPS networks across the entire island chain, there is still no answer to the central question. Was this week the whole story, or is it the opening chapter of something worse? That question is still open, and the fact that it is open, the fact that we are sitting inside the uncertainty rather than past it, is itself a kind of historical moment. In 2011, there was no sitting inside the uncertainty. The warning came first, and nobody knew what it was. The foreshock happened, and 51 hours later the main event followed, and the opportunity to recognize the pattern in real time was lost. This week we know what the pattern looks like. We know the history. We have the language to describe what we are watching. We have the instruments to measure it. We are aware in real time of what this situation might be. And that awareness, however incomplete, however frustrating in its lack of certainty, is a form of progress. Not the progress of being able to predict earthquakes, which we still cannot. Not the progress of being able to prevent disasters, which we still cannot. But the progress of being present to the possibility, of knowing what we do not know, of maintaining the vigilance that the situation demands rather than the reassurance that the situation invites. Because the most dangerous moment in any foreshock sequence is not the main event. The most dangerous moment is the window before the main event, when the initial earthquake has been logged and analyzed, and the news cycle has moved on, and the evacuation orders have been partially lifted, and people are returning to coastal areas, because the first wave was only 40 centimeters, and surely that means it is over. That is the moment that kills people, not the earthquake itself, not the tsunami itself, but the decision, made in a window of false calm between warning and catastrophe, that the warning was the whole story. Japan is refusing to make that decision this week. The monitoring continues. The advisories remain in place. The scientists are still watching the data feeds. The GPS stations are still streaming. The seafloor pressure sensors are still reporting every fluctuation of the water column above the fault. The tide gauges along the Sanraku coast are still measuring every centimeter of water against the harbor walls. And the aftershocks are still happening. As these words are being spoken, the seismic networks across Japan and around the Pacific are recording new events. Each one is a fragment of data. Each one is a sentence in a story whose final paragraph has not yet been written. The story is still being written in real time, by the rocks beneath the Pacific, by the instruments we have deployed to listen to them, and by the scientists who are trying to translate what those instruments hear into language that can inform decisions and save lives. The answer exists. It is there in the stress state of the subduction interface. It is there in the pattern of locked and slipping fault patches. It is there in the microscopic deformations being recorded by GPS stations and seafloor sensors and orbital radar systems. The answer is present in the data. We just cannot read it clearly enough yet to know what it says. And when we can read it, when the picture finally sharpens into something that admits a definitive interpretation, it will be either because the situation has resolved itself quietly, and this week fades into the archive of events that did not become the disasters we feared, or because the ground beneath northeastern Japan has moved again, and the question that seismologists could not answer in real time has been answered by the Earth itself in the most irreversible way possible. That is the reality of living on a planet with fault systems like this one. The machinery that shapes the surface of the Earth operates on timescales that make human planning feel almost meaningless. The Pacific Plate was pushing before any of us were born. It will be pushing after all of us are gone. The debt accumulates, the fault holds, and eventually the fault lets go. We cannot stop it. We cannot predict exactly when. We can only watch and prepare, and refuse to be caught looking the other way at the moment when the watching matters most. This week, every eye that science can bring to bear on the Japan Trench is open. Every instrument is running. Every data pipeline is active. Every researcher who has spent their career studying this fault system is watching what it does next. Because this is the moment they have been preparing for, not with dread, but with the hard-won knowledge that the Earth gives warnings, sometimes, and that the only appropriate response to a warning is absolute, sustained, unblinking attention. The story is not finished. The monitoring continues. And the question that is the real story of this week, the question that every sensor and every satellite and every GPS station and every seismograph on this planet is trying to answer, remains open. Was this the main event, or was it the warning? We do not know yet, and in that not knowing, the most advanced civilization in the history of this planet is doing the only thing it can do. It is waiting, it is watching, and it is refusing to pretend that it is not afraid.